for reasons I don't entirely understand, the video is acting a little odd. I think it's recording now, but it's not coming up on this screen. But anyway, Friday. We're going to continue on chapter 3. So, thermodynamics, you have homework that's going to be due Friday. In just a second, I'll ask your questions. And then for chapter 3, the homework will be due on the following Friday, September 27th, followed by an exam on Monday. So you won't get your homework for chapter 3 back before the exam. You will have the solution for the homework back before the exam. One thing I wanted to mention on chapter 2, homework, before I ask for general questions, is on problem 29C. I'll write it over here. Problem 29C was a little bit of a hard one where you had to have a guess that's given and you're going to plug it into your differential equation. And there's a couple of properties of hyperbolic functions that you may want to have. You could look them up in a handbook, but let me just note a couple of them. First of all, the derivative of the hyperbolic tangent is equal to the hyperbolic secant squared. So that might be useful to you. And another one is that there's an identity similar to trig identities for hyperbolic functions. Secant squared, hyperbolic secant squared, plus hyperbolic tangent squared is equal to 1. And with those two, you should be able to solve the problem and verify that it's a solution. And one other thing I wanted to mention, the book writes out the guess, or the solution, and it looks like this: mg over k square root, hyperbolic tangent, and then what's inside the hyperbolic tangent isn't real clear in the book. It's kg over m square root all times t. That t looks a little bit like it's in the denominator or inside the square root. It's supposed to look like that. So that's a little hint. And if you ever need trig identities or mathematical identities, this is one good source. Schwamm's outline is what I use for 99% of my needs for mathematics. It's cheap, it's easy to carry, and it's got almost everything you ever need, including this information. So if you're ever looking for a cheap way to have a good source of mathematical information, it's not required for this class, but I just wanted you to know about it. Okay. Other questions about homework that is due on Friday? Yes?
For the first one, what density do we assume of the cells?
What is pardon?
What, for the very first one, number 3 part A, what density do we assume for the cells?
You use the density of water. Almost all tissue is going to be essentially the density of water. That's going to work unless you're looking at very slight variations between water and other tissues. Other questions on homework too? Yes?
When finding the metabolic rate of chickens and humans, do we just use the chart that we were given?
The equation in the book, you could either use, I think the one that we derived in class and in the book are very slightly different. You could use either one, would be fine. But the idea is you're going to use the scaling relationship for basically metabolic rate or specific metabolic rate. Use the appropriate one for mammals. I think there might have been 2 or 3 in the book. Other questions about the homework? Going once? Got one.
On 29 part A, it says it wants you to write the differential equation for b as a function of t.
Yes.
The equation I got was b with respect to t equals mg minus kb squared. Is that what I should be looking at?
That sounds like you're on the right track.
Okay.
I won't just state the answer, but I think you've got the general idea correct.
Okay.
It's going to look very similar to what we did in class, except that it's going to have a b squared in there. Anything else? Okay, as usual, you can catch me either after class in my office hours or send me email or stop by. Is that a question?
For the same question for 9, would we be using gravity or acceleration? Like, would it be
Well,
constant
you're going to have F equals ma. A is going to be acceleration, dv dt, and one of the forces is the force of gravity. So you'll get an mg on the side that has the forces, and you'll get an ma, or dv dt, on the side that has mass times acceleration. Okay. Anything else? All right, then let us begin chapter 3. Yes, I think I told you in chapter 3. Oh, let me say one more thing. I sent you all practice exams for exam 1. And the game plan is to spend at least one class, and maybe more, towards right before the exam, going over those practice exams, and then you'll finally get the solutions to them, written solutions, sent out to you. So take a look at those if you want to get an idea of the format of the exam, how long it is, the types of questions. You can look at those exams, and then we'll discuss them in more detail as we get close to exam 1. It's over chapters 1 to 3. All right, so what I want to talk about this class is we're going to talk about the Boltzmann factor. We're going to skip the first few sections of chapter 3 on really a long derivation of the Boltzmann factor almost, and we're just going to take the Boltzmann factor as a given. So let me see what it looks like here. This is Boltzmann factor. And the Boltzmann factor says, suppose you have a bunch of discrete energy levels. So you have energy level E1, E2, E3, E4, and so on. There could be a whole bunch of them. And this then represents increasing energy as we go up. So these would be microscopic, sort of molecular energy levels. What we're going to do is we're going to talk about if you're in thermal equilibrium. So that's a big assumption. Thermal equilibrium, you have a probability of being in the ith level. So this is 1, 2, 3, I. So I would be, that's the same as saying the probability of having energy, EI, is going to be a constant, e to the minus the energy of the ith level over kT. That's the Boltzmann factor, is usually referred to this exponential factor right here. And let's now talk about what these different symbols mean. Okay, first of all, P is a probability. So it's a dimensionless number, and it's going to go between 0 and 1. And there's going to be many cases where you're going to want to what's called normalize the probability. That is, you know that if you sum up over all the possible states, probability is 1. That's just saying that the particle, let's say the electron, has to be in one state, one or the other. So the probability of in each state when added up gives you 1. You're certain it's there in one of them. So we're going to be using that normalization condition to solve basically for this constant C in many cases. And C is a constant. That means it's independent of the energy level, so it doesn't depend on the energy of any one given level. E is the energy. Okay, the energy would be in joules, but sometimes when we're dealing with molecular energy levels, we're going to use a different unit. We're going to use the electron volt, where you have so the electron volt, which is just another unit of energy, even though it says volt, electron volt, it's a unit of energy, and it's to be related to the joule by 1 electron volt is 1.6 times 10 to the minus 19 joules. You might say, well, this looks like the number that's the charge of an electron, and basically that's how they got the definition. But for our purposes, it's just a conversion factor. 1 electron volt is 1.6 times 10 to the 19 joules. So a joule is a big unit of energy, and oftentimes it's not appropriate for studying atoms and molecules, which is why we have a much smaller unit of energy for that case. All right, T. T is the absolute temperature. Okay, so T is going to be in, I don't know what that said. T is going to be in Kelvin. You have to use absolute. If you use Celsius or Fahrenheit, you're going to get the wrong result. Blank screen timed out. Press to return. Blank screen on. There we go. So T equals 0 is absolute 0. So it's the absolute 0 of thermodynamics. If you have temperature equal to 273 Kelvin, that's the same as 0 Celsius. And that's going to correspond to when ice melts. So it's the same as 32 degrees Fahrenheit. That's the temperature that ice freezes or ice melts. If you're going to go up to 310 Kelvin, that's body temperature. That's 37 degrees Celsius or 98.6 degrees Fahrenheit. That's the temperature we're going to use almost all the time because we're going to be dealing with biological objects. At least when we're dealing with mammals and other warm-blooded mammals, they're all going to sit at 310 Kelvin. And finally, if you go up 100 degrees above this, 373 Kelvin, you get to 100 degrees Celsius, and that's going to be when water boils, or 212 Fahrenheit. So in general, if you want to find the temperature in Kelvin, it's going to be equal to temperature in degrees Celsius plus 273. Have to use absolute value, absolute temperature when you're dealing with the Boltzmann factor. Some equations, especially when we're taking derivatives of temperature, which we'll do in a little bit later in the semester, doesn't matter whether you use Celsius or Kelvin because the size of the degree is the same. 100 degrees separates water freezing and water boiling, just like 100 degrees separates it. But so if you're taking derivatives of temperature, it doesn't matter whether you use Celsius. Difference is the temperature. But when you're using the temperature itself, the Boltzmann factor has to be absolute. And finally, K here. K is the Boltzmann constant. Which is just a constant, which is equal to 1.4 times 10 to the minus 23 joules per Kelvin. And it's going to be basically a conversion factor that goes from energy to temperature. So whenever we're kind of converting between the two, we're going to be using the Boltzmann constant. You can also write this out if you want to in terms of electron volts, and just to write down its value. 8.6 times 10 to the minus 5 electron volts per Kelvin. It's going to be the same thing. So these are what these symbols mean when we're talking about the Boltzmann factor. So what we're going to do now is we're going to look at a bunch of examples to see how we can use this to kind of learn about different applications to medicine and biology. But before we do, let me just ask you in general if you have a question about the Boltzmann factor before we go on. All right. Then we'll do our first example, which is probably our most important example, which is going to be magnetic resonance imaging. So I'm going to get rid of all this, and then we're going to talk about MRI. Now the nice thing about this example is that it's a two-state system. There's two states involved. There's the spin can be up parallel to a magnetic field or spin down anti-parallel. So it can hardly be simpler than a two-state system. A one-state system would be trivial because there's only one state. So probability to be in that state's 1 and there's nothing interesting. But the two-state system actually has some interesting dynamics in it. It's worth looking at. So this is problem 3.31 from the book. 3.31 is not in your homework assignment, so and it has to do with magnetic resonance imaging. So the whole idea of magnetic resonance imaging, and let me say that if you're interested in MRI, if you take medical physics the second semester of this sequence, you'll spend the whole chapter 18 in the book, on MRI. We're just going to touch on the ideas related to Boltzmann factor here today. So, like I said, there's two states. You can have spin up or spin down. This is the spin of the electron as it sits in a magnetic field, which we're assuming is going up with strength B. So, and the spins have a certain magnetic moment, mu, associated with them. That's the magnetic moment of an electron. So it's bringing in some ideas from electricity and magnetism, hopefully you remember from your introductory physics class. But the bottom line is we have two energy levels. And the lowest energy level corresponds to the spin up. So if spins are aligned with the magnetic field, that's the most stable state. That is the lowest energy level. And its energy is going to be minus mu b. It's minus, it seems kind of counterintuitive. The spin up has a minus, but you want to spin up is the lowest energy level. So the minus is going to actually be the more stable level. And then the spin down is going to be plus mu b. So the energy difference between the two states is 2 mu b. All right. Now, what would be an expression for the probability that you're in spin up? So what did we say from the Boltzmann factor? Who's got it in their notes what the expression was?
C e to the negative energy over kT.
Okay, and this is for spin up. So what's the energy for spin up?
Negative mu b.
All right, so the minus sign here is going to cancel the minus sign in the Boltzmann factor. So it'll be mu b over kt. That's the probability of being in the spin up state. And the probability of being in the spin down state is going to be the same, except now the energy is plus, and there's a minus sign in the Boltzmann factor, so you get C e to the minus mu b over kt. So those are two expressions for the two spins. Now, we don't know C. How did I say we're going to find C?
The condition, the sum of the probabilities 1.
The sum of the probabilities has to be equal 1. So that means C e to the mu b over kt plus C e to the minus mu b over kt is going to equal 1, since they're probabilities. And we can solve for C, and we'll get C is equal to 1 over e to the mu b over kt plus e to the minus mu b over kt. And there we have C. So we can stick C into here, and we have expressions for the probability for being either up or down. And now, let us pause for a second and see if we can look at some special cases and understand these probabilities. Okay, first case. Suppose we have a very cold system. Probably not a biological system, but suppose you're doing MRI on a crystal and you put it down into real cold temperatures. You're eventually going to have your two states. You're down and you're up. And your KT, now KT, remember in KT has the same units as energy because it's E, it has to be a dimensionless number. So KT is really the amount of thermal energy that you expect each spin to have. So it'll have sort of a random thermal energy. So we're going to say that KT is very small compared to the separation between energy levels, which is 2 mu b. That's what it means to be cold. Now, what do these probabilities become if you're very cold? So, if you're very cold, T is small, particular KT is less than mu b. This is a small number up here. If that's a small number, first of all, what does C become? T is a small number, I should say, because it's cold. So actually, the exponent is a large number. So which of these two terms is going to dominate? If mu b over kt is big. This is the mu b much larger than kt. That's what it means to be cold. Okay.
That term.
That's going to be huge, e to a huge number. This is going to be tiny, e to the minus a huge number. This term is going to be utterly negligible. And you're just going to have c is going to be this. And the probability spin up also has a huge number, but it's exactly the same in the numerator and the denominator, because this is c. So you cancel them out, and you're just going to get 1. This is driving me nuts. Press through it. Okay. And what do you get if you have for p down? Well, you can almost say immediately it's going to be 0 because the sum has to be 1. It's actually not going to be exactly 0, just like this is not exactly 1, because this is going to be a tiny number over a huge number. So you could write it as some exponential minus 2 mu b over kt, but the point is that's a lot less than 1. That's going to be very small. So when you're cold, that means all the spins here are down here in the upstate, and there's essentially none in the downstate. You're saturated. You've saturated into the ground state. So that makes sense. So these equations seem to have something that makes sense. Let's look at another limit. Let us look at the limit. Here's your spin up. Here's your spin down. I should write them closer together. And your kt is going to be big. So you have a lot of thermal energy. So this is the limit when mu b is a lot less than kt. So now it's very hot. Okay, so what is p up in this case? Mu b is a lot less than kt. So that means you get e to a very small number, e to the close to 0. What's e to the 0? 1. And so is e to the minus 0. So you basically have 1 over 1 plus 1, or 1 over 2. You're going to have 1/2. And it's going to be the same thing for p down, which is going to also be 1/2. So when you're very hot, that means the spins up. Half of them are up and half of them are down, except it's not exactly a half, because you're not going to get something that totally cancels out. You might have a very, very slight preference for being in the spin-up state. The ground state's always going to be the highest, but it's going to be nearly the same in both cases. So you're going to have just about half the spins up, half the spins down, with maybe a tiny, tiny fraction dominating in the up versus down. So, which of these two limits do you think applies to magnetic resonance imaging? So I'm just going to take a vote by hand. It doesn't really matter, but take a guess. How many of you think magnetic resonance imaging operates in this regime? Raise your hand. Okay, you got 1 or 2, maybe. How many think magnetic resonance imaging operates in this regime? Okay, got a little more. And in fact, you folks are right. Magnetic resonance imaging operates in this regime, which means that it's really amazing that we can do MRI, because when you put on this magnetic field, you still have almost half the spins up and half the spins down. So there's really no net magnetization except for that tiny little bit of preference, a spin up over spin down. So let's see if we can quantify that a little bit. So I'm going to put some numbers to this. All right. We're going to make mu is for an electron. Excuse me, we're not doing electrons. Magnetic resonance imaging works on the protons, a proton spin. And it's the spin of basically the protons, mostly the ones in water. So this would be the spin of the hydrogen nucleus, or proton, times 10 to the minus 26 joules per Tesla. That's the funny unit. There are other units you can write a magnetic moment in, but the most useful for us is joules per Tesla. Magnetic fields. Anybody know how big a magnetic field is in a typical magnetic resonance imaging machine? Take a guess. 9. That would be actually like a super research MRI unit, but they do have them that big. When I was you guys' age, the typical magnetic field would be 1.5 Tesla. Then they went up and you saw a lot of 4 Tesla machines, and now you're occasionally even seeing 7 Tesla machines. I'm just going to take a nice round number for in the average of those 2 Tesla. Okay? Always going to be a few Tesla is going to be. So, mu B, which is now going to be energy, because joule per Tesla times Tesla, is going to be just twice of this, 2.8 times 10 to the minus 26, and that's going to be joules. If I wanted to write that in electron volts, I can do the conversion, and it can be written like this, 0.0000018 electron volt. Okay, let's try now and see kT. We already know what K is, 1.4 times 10 to the minus 23 joules per Kelvin. What did I say? Be a little careful. T over here is a unit Tesla. T over here is a temperature. It's going to be Kelvin. What did I say our body temperature was? 310 Kelvin. So you multiply those two together, and you get mu B. KT is equal to 4.3 times 10 to the minus 20. Guys, but look, you still have young eyes. Minus 21 joules, which is the same as 0.027 electron volts. 0.027, that's approximately 1/40th of an electron volt. If you ever want a rule of thumb, just remember how big thermal energies are, how much energy every atom in your body basically has, just due to its thermal motion. It's roughly 1/40th of an electron volt. All right, so what you see is that this is 0.027 is much larger than 0.0000018. So that's why you're in this limit where it's really a very, very hot system. KT is much greater than UB. Okay, so now let's look at something. Let's look at the ratio of the probability to up to down. And you might think this is just going to be 1, but I want to try to do it a little more accurately. Remember, the probability of spin up had a constant e to the mu b over kt, and the probability of spin down had the same constant e to the minus mu b over kt. So the constants cancel, and this just becomes e to the 2 mu b over kt. Now, this is a small number, I grant you. A small number means we can expand the exponential, and what did we say the Taylor series is for an exponential? What do you think?
1 plus t.
It's exponential. If e to the x would be 1 plus x, or e to the t would be 1 plus t. So this is approximately 1 plus 2 mu b over kt. And that means this would be 1 point, and if you take twice of this and you divide by this, you get a very small number. You're going to end up getting 0.0000133. So this gives you an idea. This is not exactly 1. There is more in the up position than in the down position. But it's only like 1 part in roughly a few parts in a million over preference for being the spin up versus spin down. But without this, you wouldn't be able to do MRI, because MRI needs a net spin, and the only way you can get a net spin is to have more in the spin up than the spin down situation. So you're dealing with just this tiny little extra bit. All right, and since we're going to have a net spin, let's look at the magnetization. So the net that means your net spin of a piece of tissue. So the magnetization, we'll call it M. It's going to equal, well, it's going to be the sum of all the individual spins. So there's going to be certain spins that are going to number that are going to be in the up direction times mu. And then there's going to be some that are pointing down. So plus the number in the down direction times minus mu, because they're pointing downward. Now the number up and number down, that's just the total number of spins you have times the probability up or the probability down. So the number, this is now the total number of spins. This is annoying. Turn, black screen on. Okay. Total number of spins times the probability of up will be n up. Probability of up is going to be up, and the mu's are going to come out, so I can take that out too. Mu times n, and then you get a minus sign here, so minus probability of down. And we already wrote this expression for probability of up and probability of down. So it's going to be, probability of up is e to the mu b over kt divided by e to the mu b over kt plus e to the minus mu b over kt. And spin down has this minus sign here, minus, and spin down had a negative sign in the exponent. So it'd be e to the minus mu b over kt divided by the same constant. And what we found is an expression for the magnetization as a function of temperature and magnetic field strength. Now, we were just talking about, in the homework, hyperbolic tangent function. Hyperbolic tangent function is actually defined as e to the x minus e to the minus x divided by e to the x plus e to the minus x. So you could write this, if you wanted to, as mu n hyperbolic tangent of mu b over kt. But we'll probably just stick with this because you're a little more probably familiar with exponentials. Okay, so I want to do the same thing we did before. We're going to look at limits. Let us see, first of all, if you have a low temperature. Low temperature means T is really small, in particular mu b is a lot bigger than kt. So this is going to be then a real big number. Mu b over kt is a big number. So what does this expression become when mu b over kt is huge? Somebody help me out here. Let's see. How about Connor? Is that you? Yeah. What does this become when mu b over kt is giant?
Very large negative number, very large positive number.
Yeah.
The top basically go to zero because they're both going to be.
Well, this is good. The size of this number, the magnitude is going to be large, but it's got a minus sign. What would e to the minus 1,000 be?
Very, very small.
Very small. This would be negligible, and so will this. This will be huge, but so will this. It'll give you 1, and you'll just be left with mu n. So magnetization is mu n. How do you interpret that? Well, that's when all the spins are in the ground state, they're all pointing up, and they're all lined up together. So the total magnetization is just the number of spins you have times the magnetization of any one. So they're all lined up. It's saturated. It's saturated in the spin up. Can't get any larger. It's the largest it can possibly be because all the spins are aligned. All right. Let's see what this says for high T, because this is the magnetic resonance limit. So this is going to be an interesting one. So, who else wants to help me here? What happens when T is really big, so mu b over kt is a tiny number? What are we going to do? Lily, what are we going to do? If you have e to a real tiny number, you could just say 1, and this one's 1, and you get 0. But we want to try to do a little better than that. Saying 0 is too rough of an approximation. So what do you want to do if you have if you want to try to get a little bit better approximation? What can we approximate the exponential as? Anybody?
0.
Well, you approximated this a Taylor series, so it's going to be 1 plus something small. So remember, e to this thing is going to be approximately 1 plus this exponent. Minus, and this is going to be approximately 1 minus the exponent. So you're going to use your Taylor series, and you get 1 plus mu b over kt minus 1 minus mu b over kt. And the new denominator, we do the same thing. 1 plus mu b over kt plus 1 minus mu b over kt. And if you look at the 1s, you just indeed get 1 minus 1, so it doesn't give you anything. On the bottom, it gives you 1 plus 1, or 2. So you get, on the bottom's easy, you get mu n, you're going to get a 2 downstairs, and these two terms cancel. Upstairs, the 1s cancel, but this is a minus and this is a minus, so you get plus. So you get 2 of these terms. You're going to get 2 mu b over kt. So the 2's cancel, and you just get mu n times mu b over kt. This is the magnetization. And you see, you had to go a little beyond just assuming the exponential is 1 to get this result. Mu b over kt, we already decided that this was a small number. That's our assumption, high temperature, which really means mu b is a lot bigger than kt. Mu b is a lot smaller than kt. So you're going to get mu n, what we had before, times a real small number. So it's much smaller than it was at low temperature. But here's the interesting thing. Is, well, first of all, we have an expression that actually tells us what the magnetization is. And we also find that the magnetization increases with magnetic field strength. So why do you think they're building these magnetic resonance imaging machines that have stronger and stronger magnetic fields, so up around 7 or 9 or 11 nowadays? Well, one of the main reasons is because they'll give you a larger net magnetization. You're forcing the spins to be more in the upstate and less in the downstate. So in this way you win by going to stronger and stronger magnetic fields. So that's one of the reasons why you're driving MRI, is driving these stronger fields. You might say, well, we can also reduce the temperature. And that would do the same thing. And that works great if you're dealing with non-living substances like a salt crystal that you want to take an MRI of. You can do it in liquid nitrogen. But it just doesn't work for humans because we're warm-blooded animals. So even if you could change our temperature a little bit, a few degrees out of 310, it'd be a negligible effect. So we can't play with any of these other numbers because they're all fixed. N is basically the number of spins. That's presumably fixed for you. The only thing you can play with is B, and people are trying to make B larger. So we learned a little bit about magnetic resonance imaging from looking at the Boltzmann factor. It's a classic two-state system. Questions about that? Yeah.
So you said that it would give you a higher M value. Would that correlate to like a higher quality image from the MRI?
It would correlate to a better signal-noise ratio for your magnetic resonance imaging machine, which would then let you do fancier and fancier methods because you got a little signal-noise ratio to play with. So yeah, it would. There are other factors in addition to just this, so I don't want to make it too simple, but basically it means you have a better MRI machine. But it's kind of difficult to make magnetic. I mean, I think, why don't we just make 100 or 1,000 Tesla machine? But there gets to be some safety issues, and there gets to be a lot of technological issues when you're trying to make machines with that high of a magnetic field. I mean, this is already a pretty high magnetic field. I don't know if any of you ever had an MRI taken. If you go in with your with your credit cards in your wallet, they're erased. If you go in and happen to have screwdriver in your hand because you're going to go try to fix it on our machine. It'll yank the thing out of your hand and go flying into the machine and probably break something. I mean, it's a big magnetic field already. You try to make it even bigger, all these problems get more complicated. All right, so let's do another example. Unless there are any last questions about this one. Okay, I'm going to stick with a two-state system, but our example 2 is going to be looking at evaporation, which you might think doesn't have anything directly to do with life, but I mean, we live and breathe the air around us. How much water it has in it is important for life. So we're going to consider a closed system that's partly liquid. So think liquid water. And it's going to be partly gas above the liquid. So up here is going to be gas, that's just water vapor. So this is going to be the two-state system. You can have your atom, your molecule of water, could be down here in the liquid state, and we're going to give that energy 0. Now energy, oftentimes, especially with potential energy, you can set your own 0, and what matters really is differences between the energy levels. So we'll just take this as energy 0. And in order to get that water molecule to evaporate out of the liquid, it's got to come out, and there's forces that are holding it in the liquid, so to come out takes a certain amount of energy. So you're going to have an energy here, which I'll call epsilon, a certain amount of energy to be in the gas state. Once you get out there in the gas state, you can bounce around. You had to give it a certain amount of energy to get out of the liquid. So it's a two-state system. So what we want to do is we want to write down the probability to be in the liquid state. What's the probability of using the Boltzmann factor to be in the liquid state? What do you think? Okay, so what was the general expression for the Boltzmann factor? Anybody?
P equals C e to the negative energy over KT.
Okay, and the energy is just 0 in this case, so e to the 0 is 1, so it's just a constant. And the energy, or the probability of being in the gaseous state, is just that what you just read to me. C e to the minus epsilon over KT. Okay, Samantha. We want to figure out what C is. How did we do that last time? That's right, we normalized. We said the probability, it's got to be in either the liquid or the gas state. There's no other choices. The sum of the probabilities has to be 1. So I'm going to add these two. Instead of equal to 1, I can factor the C out. I'll give you a 1 plus e to the minus epsilon over KT equals 1. So C becomes 1 over that sum. And in fact, if I want to, I can multiply through by e to the plus e to the KT. So I'm going to do this all kind of in my head here. C is equal to e to the epsilon over KT over e to the epsilon over KT plus 1. I basically brought this down, and then I multiplied through by e to the plus epsilon over KT. Just because I like it a little better to avoid negative exponentials. Now, so this is an expression for C, so we can basically find what the probability of the gas. That's our main question, is what's the probability to be the gas? So the probability to be the gas is going to be this times this thing. Well, here you got e to the plus e over KT, or epsilon. This is e to the minus epsilon. Add those together, you just get 1 over, up with the 1 first, e to the epsilon over KT. And why do I care about this? Because this is really telling you what the relative humidity is. I mean, something proportional to the relative humidity. More probability that you're in the gas, the more humid the air is. So, what I want to do now is I need to know what this energy is. And the energy, epsilon, so that's the energy it takes to pull the molecule out, is about 0.43 electron volts. So, I want to try to learn something about this system. And then what we're going to do is we're going to imagine now that, one thing that we know about air is that the amount of water it can hold depends on temperature. This is why there's dew on the grass. At nighttime, the temperature goes down, it can't hold all that air, it comes out, and it goes back into the liquid state, and you got water all over the grass. So let's see what happens here. Temperature equals 300. A little bit less than your body temperature, but sort of room temperature. You're going to have KT is approximately, and this is at 1/40th of an EV, but I want to be accurate in this case, 0.2625 electron volts. And if I take epsilon over KT, I'll take 0.43 divided by that. Well, this is 0.43 is big compared to this. It's in the denominator, so I get something big. I get around 16.38. So the probability of being in the gaseous state is going to be 1 divided by 1 plus e to the 16.38. Well, e to the 16.3 is a pretty big number, but not gigantic. And that's going to be in the denominator, so the probability of the gaseous state is going to be pretty small. You're going to get 0.077 times 10 to the minus 6. Pretty small probability that you're in the gaseous state, but that's what you expect. Most of the water is in the liquid state. Now, what's interesting is when we look at a different temperature, because that's going to tell us whether you're getting more or less water into the gaseous state. So let's look now at 310, which is, these are both in Kelvin. This is body temperature, but it's also the temperature on a really hot day. So you go out on a really hot day, and how much water can is in the air? Well, KT is now going to be almost the same, just slightly bigger. It is, 300 to 310 is about a 3% increase. So KT is going to increase by about 3%. And so I wrote it real accurate so we can see that. 2713 EV. Slightly more thermal energy. Epsilon over KT is, again, epsilon is just this constant. T changed by about 3%, so epsilon is going to change by about 3%. It's going to go down 15.85. Okay, here's the interesting thing. If you change the exponential by about 3%, you're going to have a really big change in your probability of being in the gaseous state. It goes up to 0.131 times 10 to the minus 6. Well, that is almost a factor of 2 larger. So you had a 10-degree rise in temperature, which really amounts to a 3% change in the temperature, and you get almost a factor of 2 change in how much water is in the air. This is an example of the Boltzmann factor at work. And it works this way because you're dealing with really big numbers. You're dealing with big numbers in the exponent. So let me just show you a simple mathematical fact that will show you this. This is going to be a big number, 101. I can write that as e to the 1 times e to the 100, which means this is just e to the 1. That's e, 2.7 times e to the 100. So, if I compare the two, I find that e to the 101 is 2.7 times larger than e to the 100, even though there's just a 1% difference between the exponents. 1% difference between the exponents, almost a factor of 3 difference in the actual value. That's what happens. That's the same thing that was happening down here and caused this probability to go up so fast. So when your factor here gets big, you can see these kind of effects. It becomes very sensitive to the temperature. And that's why the amount of humidity in the air is so sensitive to the temperature. It's Boltzmann factor at work. Questions on that one? All right. So let us look at another. Let's look at the atmosphere. We talked about the atmosphere a little bit on one of the first days of class. Okay, so the atmosphere and all the air molecules. Let's just imagine the atmosphere is pure nitrogen for our purposes. It's 80% nitrogen, so it's a pretty good approximation. The energy is going to be mg times the height. Now, you might say, wait a minute, now this energy can be a continuum of values, it's not discrete energy levels. Well, the whole system still works. You just, instead of summing up over all the energy levels to get the normalization, you'll have to integrate over the energy levels. But the whole idea works. So the probability, at least some sort of probability density, at being a height h is c e to the minus mgh over kt. That's the Boltzmann factor. Okay, so we're basically going to stop there, except we're going to say that in general, if you have an h here, the whole thing has to be dimensionless. So it's going to have to be written as h over lambda, where lambda is some length constant, and we can just pick lambda out. Lambda is kt over mg. And this describes the probability of a molecule being in our atmosphere, and a probability will translate in sort of a density, which will translate into a pressure. So it's really telling us about the air pressure, even though technically it's the probability. There's an assumption here. The assumption is that the temperature is the same throughout the whole atmosphere. That's not quite true. It changes as you go up. It gets colder as you go up. But if we make the approximation the temperature is constant, we can come up with an exponential atmosphere. And let's see if we can get some idea what kt over mg is. 1.4 times 10 to the minus 23 joules per Kelvin. We have to guess what the average temperature of the atmosphere is. I'm just going to put in 300 Kelvin. That gets pretty good until you get up real high. And mass. Well, we need to know the mass of the nitrogen. Remember, nitrogen's a diatomic molecule, so technically we need the mass of the N2, nitrogen diatomic molecule. So there's two of them. Anybody know the molecular weight of the most common nitrogen isotope?
28.
Pardon?
28 atomic unit.
14.
Oh, I think
14. There's 7 protons. That's what makes it nitrogen, and there's 7 neutrons. So its total is 14. So you get 14 protons and neutrons in each nitrogen nucleus. There's 2 of them, because it's N2. And then there's the mass of a single proton, 1.67 times 10 to the minus 27 kilograms times G, 9.8. Do this calculation and you get 9200 meters, or about 9.2 kilometers, which is pretty close to what we were talking about on the first day of class. You go up roughly the height of Mount Everest, and that's sort of the length constant over which this decays. And it all just came out of the Boltzmann factor. So the atmosphere is really the Boltzmann factor at work. Yes?
Where did you get the mass again? I see where you got like a 14.
This is the mass of a single proton, or a mass of a neutron, so I looked it up. I got that. So this is a single proton, a neutron. There's 14 of them in each nitrogen. The electrons are negligible. And its N2 is the gas molecule, so that's that factor of 2. So those three things there give you the total mass of a nitrogen molecule.
Why did you choose nitrogen?
Because the air is 80% nitrogen, I just sort of ignored the oxygen. Really, you should probably use some weighted sum, where it's 80% this and 20% oxygen, which is only different by 16 here, so it's not that different. All right. Now, let's do another example. I think we have time for one more. And actually, before we do another example, I want to say a few things about some of the homework problems. So I'll do that first. Okay, so homework problem. First one is problem number 3.29. 3.29 is going to be very similar to the very first example, the MRI example we did in class. However, it's a made-up problem where you have 3 states instead of 2 states. So I just want you to go through and redo the problem, but with 3 energy levels. And the energies and the different levels are all given in the book. And analyze it and find the probabilities and find what the problem asked you for. So it's really just redoing the MRI problem with 3 levels. All right, problem 3.30. Problem 3.30 is going to look at DNA. And we're basically going to be looking at mutations in DNA. And we're going to simplify. A lot of this is making mathematical models. We're going to simplify DNA to the point where you have 2 states. You can remember DNA has base pairs that contain the genetic information, and certain base pairs bond with certain other ones. And we're going to say that there's 2 states, the correct states, when you have the correct bonding between the 2 base pairs, and then there's going to be an incorrect state where they're not the correct bonding. And we're going to make it really simple. We're going to say there's only one way to be wrong, and so we have a certain energy level for the correct state and a higher energy level for a mistake. And we're back to the 2-state system. It's just like the MRI system. And then we're going to assume that the probability, the error rate, the rate of mutations in DNA is going to go as a Boltzmann factor. So the probability of making a mistake is C e to the minus energy over KT. And you can then use that to analyze and make some estimates of what the error rate is for DNA. And you better hope that the error rate's pretty small, because if you were making millions of mutations every time DNA reproduced, we'd have all sorts of problems. But the error rate turns out to be fairly small because the energy difference is fairly big compared to KT. So that's what drives the energy rate down. So it's going to be a problem that kind of steps you through it. A 2-state problem between right and wrong DNA binding. Okay. Problem 3.33. Another 2-state system. And that is, you're going to look at hemoglobin. And hemoglobin can either be bound to oxygen, that's one state, or it can be bound to carbon monoxide, which is another state. Now, carbon monoxide poisoning is a big problem. So it turns out that the low energy state's the carbon monoxide state. If it binds to carbon monoxide, that is its lowest energy state. So if there's a lot of carbon monoxide around, you're in big trouble. That's why carbon monoxide poisoning is so bad. Now it turns out that there's one thing I didn't tell you, and that is the probability is C e to the minus E over KT for the Boltzmann factor. But C, you can have degenerate states. For instance, if you had an energy level here, there's 1 level, but here you had 3, and here you had 5, you'd pick up a factor in C would be 5 times larger for the higher energy. So technically C is not purely a constant if you have degenerate energy levels. Degenerate means the same energy. So in this case, you got a bunch of degenerate energy levels because C is going to be proportional to the concentration of oxygen versus the concentration of carbon monoxide. So what you're going to do now is you're going to look at what's more probable, binding to oxygen or binding to carbon monoxide. And it's going to depend on this energy difference between the 2 states. And it's going to depend on the concentration of the two gases. And normally, oxygen is vastly more concentrated than carbon monoxide, and we're safe. But if you just get a small leak of carbon monoxide in your basement, you can get up to concentrations to the point where the lower energy level of carbon monoxide causes the carbon monoxide poisoning. So, that will be looking at carbon monoxide. We got a couple more I want to mention. Yes?
The constant is proportional to how many generating states?
Yeah, it's going to be proportional to the number of states, which, for our sort of hand-waving arguments, is proportional to the concentration. Okay. Problem 3.34. We're just working our way through. This is looking at enzymes. Enzymes are very important in biology. So you start off with some energy level E1, and it undergoes a chemical reaction and ends up at energy level E2. But in order to get from E1 to E2, it has to go over an energy barrier. So this energy barrier is going to be basically this delta E. It's got to go over the hill in order to get down to here. Now, we're going to assume, and again, there's sometimes you have to just make assumptions, we're going to assume that the rate of this reaction is going to be a Boltzmann factor, e to the minus, where delta E is the energy gap. So, the problem asks you to analyze this case for a certain delta E, and then you're going to look at another energy gap where you lower this slightly. You don't change the initial or final states, you just lower your delta E. And if you lower it just a little bit, you're going to get a big change in the rate. It's kind of that e to the 101 is equal to 2.7 times e to the 100 effect. You're going to be able to see that slight changes in this energy level, energy hill, is going to give you really big changes in the rate. And that's why enzymes are so effective. They can just change the protein interaction slightly, but just a slight change in that is going to have a big effect on how fast the reactions occur. So, and finally, problem 3.41. So you got 5 of the homework problems about Boltzmann factor. You're going to have something that looks just like the Boltzmann factor for the atmosphere. E to the minus m GH over KT. And basically what you're asked for is to find that length constant, just like what we did in class. However, you're going to do this for viruses and not nitrogen atoms. So suppose you had your whole atmosphere was now just little virus molecules. How would they be distributed through the atmosphere? They wouldn't all fall down to the ground. They're in thermal equilibrium, so they're bouncing around. But their mass, which is given in the problem, is going to be much larger than the mass of the nitrogen atom, which is going to mean that length constant is much smaller. So you expect these viruses to create basically their own atmosphere that's a lot thinner than our air atmosphere, and you have to calculate how thin. And it's always useful to keep in mind your approximations. One thing that is ignored in our atmosphere analysis is any sort of winds blowing around, mixing things. And that doesn't make too much of a difference for the atmosphere of the nitrogen gas atmosphere. But you're going to find that, boy, if there's a little bit of wind with these viruses, that could mix things up. So you probably, it's not a realistic case, but if you had a very still atmosphere, you can figure out how high these viruses go up off the ground. And those are 5 of the homework problems that we're going to be talking about that are going to be on your assignment. So, what's happening next class? We're going to continue with Chapter 3. We'll probably do one more example from the Boltzmann factor, and then we'll move on and talk about heat capacity. And we'll talk about that, and that will be on Friday. We'll talk a little bit more about Chapter 3 on Monday probably, and then we'll start looking at those practice exams, and we'll look at those until our exam time. So any last questions anybody has about Boltzmann effect? Okay, then I will see you on Friday, and we'll hand in the homework.